Hello, and welcome to this video on double replacement reactions. Double replacement reactions are ones where we have the cation from one element and the anion from the other element that are going to combine on the other side and vice versa. And so we see that this is really a situation where they're going to swap partners. There are three main types of these reactions that we will see occur. And so the first one is going to be one where we produce what we call a precipitate, which is a solid. And so here's an example of that. So we have silver nitrate and sodium chloride, and then silver chloride is actually insoluble or very sparingly soluble, and so it's going to form a solid. So we can have two of these aqueous solutions that end up forming a solid, and that is an indication that a reaction has occurred, something new has been formed. Another one is one where we can produce a gas. And so an example of this a lot of times is cyanide. These are kind of tougher ones. We don't really use a lot of these in class, of course, because cyanide is, well, not a really good gas for us to be exposed to. And so this is something that we would see on the other side. There would be a gas being formed. So anytime we see something new outside of aqueous being formed, we know that there's a reaction that's taken place. A third one is one that's going to actually produce water, and this is called an acid-base reaction specifically. And so here's where we have a strong base. So NaOH is actually a base, and it's a strong base because it has a hydroxide as the anion. Okay, so this OH here as the anion is that indication. And then we have an acid. Okay, the acid is something that's going to start with the hydrogen ion, so an H+. And when these end up swapping partners, we end up producing aqueous sodium chloride. So that was aqueous on both sides, but the thing that's new that we formed is actually liquid water. Okay, and so that's new. Water itself is not aqueous. Things that are dissolved in water are aqueous, so forming water means something new formed. And so these are three examples, or three different ways that we can take a look at these double replacement reactions. Okay, so what we want to know actually is these solubility rules, because we primarily look at precipitate reactions when it comes to double replacement at this point in our chemistry experience. We'll also do some acid-base reactions, but we come back and do acid-base chemistry later on. So here are the general rules that you want to know. The things that are always soluble: ammonium ion, the alkali metals, so lithium, sodium, potassium, so on and so forth down that column, and then a few of these anions. Okay, so these are the things that we know are always going to be soluble. The things that are usually insoluble are going to be phosphate and carbonate, are oxides. Okay, and hydroxides can kind of, it just depends, unless they're with one of those things that are always soluble, and of course sulfides as well. And then finally we have things that are usually soluble. So for this last one, these are usually soluble except, okay, so this is the big exception, when they are with one of these three. So there's probably more rules, but this kind of gets us to the general idea. So sometimes things are sparingly soluble. It depends upon the concentration of them, but this gives you kind of just a general overview, and we're going to use these rules in order to determine the solubility. So let's go ahead. Oh, and then finally, sulfate is soluble except when it's with these particular cations. So that is something else to consider there. Okay, so there's all of our rules. So let's go ahead and do an example for one of these reactions. So we're going to have a reaction where we are going to predict the products between aqueous calcium chloride and lithium carbonate. So, okay, so here's an example of predicting products for a double replacement reaction. So we have calcium chloride. Okay, so calcium is a 2+, chloride is a Cl-, so that's going to give us calcium chloride, and it says it's aqueous. We're going to roll with that because it is. Plus lithium carbonate. So lithium is a +1 charge, carbonate CO3 2-, so it's going to be Li2. I can get that to write a little bit better. There we go. Li2CO3 aqueous. And now what we want to do is we want to predict what our products would be. So we're going to go ahead and draw our arrow here. And then on the other side, we want to swap those partners. So lithium is a +1 and chlorine is a -1, so we just get LiCl. Okay, and the question is this soluble? Well, we know it has to be because lithium is an alkali metal, and alkali metals are always soluble, so this has to be aqueous. Now, no reaction occurs if everything on the right-hand side of the equation is aqueous. So now the question becomes, well, what happens with carbonate? And so if we look and we go with calcium carbonate, so CaCO3, there are 2+ and a 2-. Okay, if we go back to the previous slide and look at those solubility rules, we see that carbonate is usually insoluble. Okay, carbonate is usually insoluble. And so what that means is unless it is with one of these, it's going to be insoluble. Okay, and so since calcium is not an alkali metal, we know that this has to be our solid. So if we take this whole situation and we apply it to what might be happening on each side, we know that everything is aqueous except for the things that are creating this. And so we know that calcium and carbonate are actually the things that are reacting in this particular situation. So I'm going to represent this in a little bit different way as well, because we want to create a net ionic equation. So if we go back and we represent this, we know that only the things that were involved in making the calcium carbonate were the things that were reacting. So let's go ahead and take a look at this one more time. So we have calcium chloride plus lithium carbonate, Li2CO3. Okay. And then we had lithium chloride plus calcium carbonate. So we're going to represent this. We know that this is our solid. We have to balance our equation. Okay. All of the rest of these were aqueous. So let's go ahead and represent those in a little bit of a diagram. And so if I look at what happens in this first one, I have a calcium ion and I have 2 chloride ions, Cl- and Cl-. Okay. In the second one, I'm going to have 2 lithiums, Li+, and then a CO3 2-. Okay. I guess I should have put a 2+ there. 2+ on the calcium. All right, so on the other side, when these change, what are we left with? Okay, so we are left with lithium, 2 lithiums that are in their ionic form. We're left with 2 chlorides, and then we're left with calcium carbonate, CO3, and that is the new thing that's formed. And so when we write a net ionic equation, the lithium and the chloride ions are spectators. They have not changed from one side to the other. They're still aqueous. And so the only things that have changed are the calcium and the carbonate that formed calcium carbonate. And so when we write our net ionic equation, we want to represent that as Ca 2+ aqueous plus carbonate CO3 2- aqueous reacted to form CaCO3 solid. And it's really important that we balance our original equation before we do this. And there's a couple different ways that we can approach solving this problem, but that is a net ionic equation that is only representing exactly the ions that reacted in this particular situation. I hope that's helpful for you, and we'll discuss more of this in class.